Swayam Prabha. Digital India. Educated India.
So welcome to the second class of this course. Okay, so for now I see that we have already, almost the entire class there now. So we'll get started here. We have been looking at the idea of why you would like to do this course in the previous class. And in today's class, let me share my screen. We will look at a few important terms. So we will look at some basic concepts which are important for us. So couple of very important points will get covered in today's class, and we're calling them as basic concepts because these are not really going to be repeated, but they are going to be very important for this course and even for your further understanding. So the first thing that we are going to define is a thermodynamic system and a control volume. So let us say that the first thing that we have to do is to define the system on which the analysis is being done. So here we are going to call that as a thermodynamic system. And so let us say that we have a box in which to which that we are adding heat or we're doing something to that box. So the box is my system, and so that is the first thing that we have to identify, that we are going to look at the box and we are going to say that the box is my system, and which is everything which is external to the system is going to be called as my surrounding, and the two should be or are typically separated by a system boundary. So we'll call this term, we'll use this term system boundary, or a boundary, just a boundary. So just to sort of say that we have something which differentiates, there is a line, imaginary line, or it could be a real line, which is differentiating what is my system, or where does my system ends and where does my surrounding begin. So, and the boundary that we are talking about could be either movable or it could be fixed. So we could have both these scenarios. But the fact is that we have a system, we have a surrounding, we have a system boundary, and these things are well defined, and the boundary itself could be movable or it could be fixed. For example, if we are talking about a box, then everything looks like, and it's just a closed box, then everything is all boundaries are well defined. So you can think of that the cardboard which is making up that box essentially forms the walls of this cardboard, are forming the system boundary, and the system boundaries are fixed in this case. But there could also be a scenario where you have a piston, or there is something else. It could be like a balloon, which is my system. So my air which is inside is my air, and I'm trying to do my analysis on this air which is inside this balloon. And now you can see that the balloon can expand or contract. So accordingly, the system boundary, which could be like the balloon itself, which is differentiating or separating the air which is inside the balloon to the air which is outside it. So those are my system and my surrounding, and my boundary is the balloon itself. Okay, and the balloon can be either movable or fixed. And in this case, it is movable. And what we would see is that heat and work can cross the system, but not matter. And this is one important difference that we are going to see, that whether we are going to let matter cross or mass cross the system boundary or not. So in this case, we are seeing that we are not letting the mass cross the system. So whatever is inside the balloon stays there. The balloon itself can, I can deform that balloon, but I'm not allowing any mass to either enter or leave this the balloon. Okay, so but I can always heat the balloon. Okay, so in that case, I am adding certain heat. So then that means heat can cross the system boundary, or I can deform this balloon. So that means I can either do work on this balloon, and therefore again we can say that that is now crossing the system boundary. So these can be further restricted to saying that we are talking about an isolated system. So till now we have defined a closed system. Now we are going to say that it is an isolated system. It's a further restriction that I am imposing. The restriction that I have imposed till now, the most important is, or the only restriction that I have imposed in my system is that the mass will not cross the system. And that is my first type of system. The second system that we will see is where we will let the mass cross the system boundary. So under this thermodynamic system, let us have a further restriction and say that nothing crosses the system boundary. So not even heat and work can cross the system boundary. And therefore, we can say that the system is not going to be influenced by the surrounding in any manner. So if that is the case, then I will call that as an isolated system. So it is not interacting. So essentially, isolated system means that the system is not interacting or not getting influenced by the surrounding in any manner. Now, however, as we know that sometimes mass does cross, enter or exit the system. For example, if you look at the overhead pipes, there is an overhead tank. If you look at any house, your house, I mean, most of the houses would have an overhead tank through which the water comes in and comes to our kitchen or to the bathroom, right? So you can see that if I'm trying to analyze the flow in this pipe, then of course the pipe, I will see mass coming in from one side, which would be the overhead tank, and it is going out from the other side, which is the tap. Now, so can we, so of course one would say that, okay, this seems to become complex because now once mass enters or exits the system, it is going to carry along with itself some momentum. It is going to carry some energy and so many other physical quantities, like if there is some concentration of something, it can change. So you can see that now this has become slightly more complex. And I will say that, okay, can we not try to model that as still an isolated system or still a system, a closed system? So I will, instead of having just the pipe, I will like to now include the overhead tank, which may be somewhere upstream, and of course, whatever is going out. So then in that case, I will be conserving the mass, and then that will become a thermodynamic system. Can I do that? So yes, in certain cases, maybe it is possible. But just imagine that from this overhead tank, not just your house is getting supplied, but there is another house to which water is going. Now, how do I do the analysis? So you can see that it becomes difficult that to now say that this pipe, along with this overhead tank, along with the pipe which are there in the neighbor's house, all that is now forming my system. So you can say that that is one way, and that may not be, and you can see that that is also not looking like very convenient. So what we would like to say is, instead of doing this, I would rather like to have a piece of this, like a segment of a pipe, like what is shown here in this figure. And I would like to rather analyze this system, which is no longer a thermodynamic system, because we are now letting the mass to enter or exit. Okay, so mass is now being allowed to come in from this side, and the mass is being allowed to exit from the other side. So in thermodynamic system, we said that is not possible. But now, because we are realizing that it is not possible to, or it is too complex, or even sometimes it is not even possible to do an analysis, we have to go in for a slightly different approach, which we call it as a thermodynamic, as a control volume approach, where we define some sort of a volume, which we call it as a control volume, around the device under consideration, just like what you see here, like this pipe, which could be a much longer pipe, but I'm taking a small segment of that, and I'm going to say that I am analyzing things in this segment of the pipe, okay, where things are coming in and things are going out. And therefore, I mean, my control volume is this segment of the pipe. And then we have a control surface, and the surface of this control volume is essentially called as a control surface. So of course, we sometimes abbreviate them as CV and CS, and you will see that this is important concept. And as we are saying that in lot of times we cannot really get rid of having to deal with a control volume. So again, just to sort of summarize, so what we are saying, we can have two different scenarios. In one case, we call it as a system when we are dealing with a fixed quantity of mass. In the second case, we have a control volume in when we have a flow of mass which is involved, either coming in or going out or both. And we can call these as closed system and open system. Now you can see that, of course, this is again with respect to mass, and I think these definitions of closed system and open system should be now obvious to you. So this is the first important concept. So we will see that when we analyze things, we will analyze it in two ways. In one case, we will start off our analysis for a system, and then we will allow, as a second step, we will allow mass to also enter, and then we will do a control volume sort of an analysis. And of course, the control volume analysis, you will see that things becomes slightly more complex. Okay, so this is the first important idea that we have talked about in this course. So let me just pause here and see if there are any questions here.
Excuse me, sir.
Yes, please.
Sir, can you please explain the concept of control volume once again?
Okay, so what we are saying is we are considering this as a long pipe. So the figure that I am shown here, you imagine that not just a small segment, you imagine that this is a huge pipe going in from one side, as I said, maybe coming from the overhead tank and taking the water into your tap. Okay, so I don't want to analyze this entire system. If I have to do that, if I have to think of it as a closed system, then I have to include my tank and I have to include the water which is coming out from the other side. Okay, so only in that case, so whatever is coming out from the tank is coming out from the tank is going through my tap into a pan which I am collecting. Okay, so then you can say that my mass is constant and I can think of that as a system. Okay, but now instead of collecting water that is coming from the tap into a pan or a bucket, we are now letting it drain out. Okay, so now once it goes out, it can go to, it is going to the drain, and from there, let us say it's going to a river. Okay, now how do I take care of this? So if I have to conserve the mass, then I have to conserve all that and include go to my river. And then I do not know whether the mass that I'm talking about is coming from the tank, overhead tank, or it is coming from the river itself. Okay, so you can see that the trying to conserve the mass, hold on to the same mass is not going to be practical in that case. And therefore, what I will rather do in that case is to define a segment of this pipe and say that this is my control volume. So this segment that is shown here is my control volume. So I will say I am going to apply all my principles of motion and essentially my laws of mechanics to this volume. Okay, to this limited volume that I'm looking at. In this limited volume, mass is coming in as shown by this arrow, and it is leaving as again shown by this arrow. Okay, and as they come in, as mass comes in, it is going to bring in momentum and energy, and similarly, some mass and momentum is mass, momentum, and energy are going to leave this control volume. So I have to account for how much is coming in and how much is going out to be able to know how much net mass, momentum, and energy I am left with in this control volume. So I am going to write down equations for that case, and that is going to be, so this region on which I'm doing my analysis is my control volume. Okay, and this control volume I can arbitrarily choose. I can choose this pipe, I can choose half the pipe, I can choose only, I can take symmetry and say that this pipe is symmetric and therefore I'm only going to take one half of this in some way and so on. So I can choose my control volume. It's like an arbitrary volume that I'm putting, and I'm saying I am analyzing things for that region only. Okay, so that becomes my control volume, and the corresponding surface of the control volume becomes my control surface.
So how does the mass under study in the control volume will remain constant with time?
The mass of the control volume will remain constant with time. That's what you are saying?
Yes, sir. How can we say that? Like, if the conditions change, if the conditions of the control volume change with time, like temperature or pressure, the amount of the mass that the control volume contains might change with time.
Yeah, that's exactly what I'm saying. The mass is changed. So control volume is specified when flow of mass is involved. So I have to see how much is coming in. I have to see how much is going out. And if the two of them are not the same, then the remaining mass is either getting accumulated inside my control volume or it is leaving from my control volume. So that's exactly what I'm saying. So I'm not in the second case. In the first case, my mass is same. Okay. So that's what we said, that the first point in this slide that you see, the heat and work can cross the system boundary, but not matter. So I'm not allowing my mass in my control, in my system to change. Okay. But in my control volume, my mass can change. Does that answer your question?
Define system as the system and control volume are two different topics. Or control volume is a type of thermodynamic system, because we define system as something where the mass remains constant.
Yeah. So for both the cases, I'm going both of them. I mean, I'm just trying to say that how would you analyze the two scenarios? Okay. In one scenario, the mass is coming in and going out. In the other case, my mass in my system is not changing. So I'm just giving these two scenarios, two different scenarios as two different names. When the mass is not changing, I'm calling that as a system, which is what is summarized here, or it's a closed system, as you can see. Okay, my mass is not changing. And the second case, when the mass is changing, I will call that as my open system. Okay, and then we are going to do a control volume analysis. Okay,
So what
that
I'm
I'm,
saying is that in
yes,
the control volume, if the density changes with time, so the mass that the control volume contains might change with time. Na? So the quantity of mass then remain fixed.
yes. So my volume is fixed. So my region, volume by volume, I mean my region on which I'm doing my analysis is fixed. Okay, but what is inside that region, I'm not. That is not in my hand. Okay, as you are saying, the density can change. Okay, or something else could change, and therefore the mass itself can change, and therefore the mass that I am now having in my control volume is changing. That's right. So just imagine the scenario that if you have gardened, if you have watered your, I mean, watered your plants in a garden, you see that, okay, if you connect it with a hose is that pipe which is bringing in the water. So that is connected to the tap at one end, and then you open the tap and the water starts flowing into your hose, right? So that's the scenario. So let us think that I have considered my entire hose, that is my entire tube, as my control volume, because as I said, control volume can be arbitrarily chosen. So initially there is air. Okay, when there is no water, I mean initially it's all filled. My hose is filled with air. Then once I open the tap, my air is getting displaced. My water is displacing my air, and my entire eventually all my entire hose is now getting filled with water. So of course, you will see that the mass which is there is changing, and of course, not just the mass. In this case, even the species which is involved. Earlier it was air, then later on it is water. Okay, but then so that's the scenario that we are looking at. So then in this case, we are saying that my control volume could be like the entire hose through which mass is coming in from one side through my tap, and air is going out initially from the other side, and eventually whatever water I'm putting in from one side will go out from the other side. Okay. So it's only a matter of whether it's steady or unsteady, but that is a classification we are not going to get into. But yes, there is a change of mass in the control volume. So we are allowing for that. Yes.
Sir, just for the sake of definition, do we consider the system boundary a part of system or like a different entity? So in the balloon example, the air considered inside, only that is considered as a system or also the balloon?
Okay, so that's actually a very good question. So, see, most of the time you can even have an imaginary boundary. For example, in this case, you can say that this is an imaginary boundary. I have just taken out this segment. Okay, I am taking it out in my mind. Okay, there is no physical boundary which is separating out, especially from the sides which are coming in and going out. On the lateral sides, on this perimeter side, you can see that things are bounded because of the pipe wall. Okay, But otherwise, things are going in. I mean, there are no nothing which is there from this side. So you can say that in that sense, you can say that okay, this the boundary is just an imaginary thing, and it is not really a part of either. So it can be like a line or a surface which has zero thickness. Okay, so that is what is now. So it is neither a part of my system or it is not a part of my surrounding. It is something which is just separating out the two things with no. I mean, it's just a boundary essentially. Again, it's just a line example. For example, line mathematically it is not supposed to have any thickness. It's only one dimension. Okay, so that's the same thing that we are saying. It's just a surface, so it is had zero thickness. Okay, does that
Okay, sir.
answer your question?
Yes, sir. Thank you.
So I will not consider it. So in nutshell, I'm not going to consider it as either a part of the system or the surrounding. It is neither. Okay, it's just something which demarcates the two regions. Yeah, that's actually a very good question. So
Sir, what if we want to consider nuclear fission?
yeah, all that is allowed. No, let mass happen change. So in that case, yeah, okay. So then in your system, so you will say that I will now convert my mass into energy. That's the type of scenario that you are looking at, right?
Yeah, slightly. Yeah.
Yeah, so that actually, really speaking, I mean, we can also analyze that within that framework. Then, of course, one would say that okay, my mass inside, because of this nuclear fission or fusion, is now getting converted into energy. So energy is coming out, and the mass inside my system is actually reducing. So whether it is, I mean, in some sense, you can see that when these definitions are made, we have not. I mean, it's not that that scenario cannot be considered. Okay, so let me not try to give that as an answer, but you can say that okay, when this definitions were given, okay, this thermodynamics was given like in 1850s, 60s, then people did not know about this nuclear fission, and therefore we don't explicitly say that okay, that's so we can say that okay, in this scenario we are not really considering this nuclear fission or fusion type of system. Okay, although we can consider that as one of these. Okay, so we will have to consider so in that case the mass itself inside is changing and it is getting converted into energy. We can write down equations for that also in the same way that we would do. Okay, and of course you can see that the control volume approach, the first case, the closed system, is a special case, and we will emphasize that as we go along. So the whole idea is that the open system is the closed system is a special case of an open system where the mass coming in and mass going out is essentially zero, right? So even in your case that you are talking about, if you have doubt, you just consider it as an open system, and then of course the closed system is a special case of that. Why we are talking about a special closed system? Because closed system does not have lot of complications to begin with. If you can identify that as a closed system, you avoid lot of complications. That's all that we are trying to. And so that's essentially that's what it boils down to. Okay, so we can consider yours if you are not sure, like your nuclear reactors thing. Consider that as an open system. Analyze that, and if it is a closed system, it will reduce to a closed system anyhow.
Okay, sir.
Okay, so good questions. Any other question? Okay, we can always, of course, if you think of a question, if you have a question, you can always come back. So now, for now, we'll move ahead, and we will talk about this second very important concept of microscopic versus microscopic viewpoints. Let me tell you that even the control volume and control this system, thermodynamic system concept, that we introduced in the previous slides, is something that you will also see in other courses being used. Okay, similarly, you will see this idea of whether we are talking about microscopic or macroscopic also get used in a lot of other courses as well. So these are very generic ideas that we are introducing, and therefore, if you have any doubts, you please try to get it clarified right here. Now, let me start off with the following question to you: that if the room that you are sitting in, if I say that how many molecules of, I mean, of course, this air, it's a mixture, nitrogen and oxygen as the most important components. But let us say that I'm just thinking of it as nitrogen. So how many nitrogen molecules are there in the room around, in the room which is where you're sitting? So if you do not really remember, you can sort of I mean, now hopefully when you look at this answer, it will start making more sense. You will see that we talk about a few moles of the gas which are there. Each mole will occupy something like a few liters, 22.4 liters or whatever, and standard NTP, STP sort of conditions. So you will see that the room that you're talking about has something like 10 to the 24, 10 to the 25, or even 10 to the 26 sort of a molecules. That is the type of number of molecules that we are looking at. So therefore, it's very clear that we cannot describe the motion of all these molecules. Okay. So if we try to describe this motion, then we are trying to look at the microscopic description, which is, as we said, is not possible. And it is not possible because of the very large number of molecules which are there in my system. Okay. System or control volume, either of the two in this case. So therefore, what we will do is, rather than trying to provide a detailed microscopic description of each of these molecules, we will rather talk about a statistical, we will use statistical tools, and we will talk about averages. Okay. So when we talk about averages, then we talk about macroscopic quantities or macroscopic variables. We start talking about what is the density, okay, what is the pressure, what is the temperature. So you can see that if I'm looking at one molecule, if I'm saying that what is the density, it is meaningless. Okay, I'm not talking, what am I talking about? Okay, if I'm talking about again one molecule, what is the pressure or what is the temperature? Okay, again, you can see it is meaningless. So when I'm talking about something like pressure or temperature, I'm actually talking about a macroscopic variable, which means that I'm talking about not just one molecule, but I'm talking about a more larger number of molecules. And I'm talking about some sort of an average behavior or average value, which is my pressure or which is my temperature. So of course, pressure gets related to some sort of forces. So when the molecules come and impinge on a surface, for example, the momentum that they transfer to the surface is, we say that that is essentially getting manifested as my pressure. Okay. Similarly, when you look at temperature, it would be some energies of these molecules, okay, which is now we relate that to my temperature. Okay. So that is the type of, that is my macroscopic variables that that we will talk about. Okay. So you will see that, so basically the point is that when we are talking about pressure and temperature and even other quantities that we deal with, we are talking about macroscopic quantities. Okay. These are not microscopic quantities, and we are not talking about the molecular description, or we're not at the molecular level of description of our description. Now, okay, any questions here? Is this, I mean, this is straightforward, reasonably straightforward, I hope.